Hello everyone, this is DSS Zindabad and today we are going to discuss the Leetcode daily challenge which is leave similar trees. So let's jump into the problem statement and understand it. Consider all the leaves of a binary tree from left to right order. The values of those leaves form a leaf value sequence. Two binary trees are considered leaf similar if their leaf value sequence is the same. Return true if and only if the two given trees with head nodes root 1 and root 2 are leaf similar. So, after reading this problem statement, we understand first we need to figure out which all nodes are the leaf nodes. Okay. So, what is a leaf node? Leaf node is a node which does not have any children. That means the left child and the right child. After figuring out these leaf nodes in both of the trees, so let's for the time being, let's assume I've been given just one tree, right? So for understanding the problem statement, I have been given one tree and I need to figure out the leaf nodes. After figuring out the leaf nodes, I'll store them in a data structure. Now, why do I need to store them is, and why we cannot skip this process is because I need to compare it with the second one, with the second tree. First, for the purpose of comparison. Second, the sequence is very important, right? That means if we look at this example right here, so we know that the leaf nodes are the one which do not have any children. So we can say all these nodes for the first tree, for example, this is the root 1, right? So all these blue nodes are the leaf nodes of these roots. I need to store them sequentially as mentioned in the question, and that needs to be in order that is left to right, right? So that means in my data structure, 6 comes first, 7, 4, 9, 8 follows after. And similarly, this is my root 2. I need to figure out my leaf nodes. These are again the blue colored nodes are my leaf nodes, and I'll be storing them in a data structure. For the purpose of comparison, I need to see that whatever is stored, for example, I'm using a vector for my data structure, right? So, is the value similar in both the case? If it is, we'll return true, else we'll return a false. So basically, this is what the problem is saying to us. Now, let's talk about the approach. How will I form an approach for this question? The first thing that comes into my mind is that if somehow I could traverse the whole tree, right? Now, why do I need to traverse the whole tree? Because I need to figure out the leaf nodes, right? So I need to traverse the whole tree. Traversal can be again done in either DFS or BFS manner, entirely up to what you are comfortable in. After traversal, the other thing that I want to do is I want to figure out that is the given node a leaf node or not, right? So for that, what I can do is I can simply have a is leaf function which will cater to this condition and it will be a Boolean function. So after these two steps, this is the step 1, this is the step 2, I can store and then compare the data structure values. So this is the whole approach that I'll be following for this particular problem statement. Now, before jumping into coding it, let's first try run that whether this approach will work for the given example or not. Or is there any modification we require for this problem, right? So I'll quickly make one more copy here. Yes. And I'll zoom out a little bit so that we can see the approach all throughout. Yes. So now what I'll do is I'll simply have something like the main function, right? I'll have the in order code. So yeah, now before jumping into the in order code, as I talked here in the approach that we can traverse the tree in either of the ways. So for this question, I have utilized the in order traversal. Now for all those people who do not know what is the in order traversal, in-order traversal is a DFS technique, that is a depth first search technique, in which we follow the traversal fashion, that is left, then root, followed by right. So for example, at any point of time, let's take this example. If I am here, right, this is the head, the root node that has been given to me. I'll first go to the left, the most left root here. This would be whatever logic I'll write would be computed on this node, and then after computation of this node, I will go to the root, that is 5. Then I'll go to the right part, and then again we'll come here to 2, but 2 will not be computed directly. It will remain in our stack space. We'll again go to the leftmost root. So this is how the in-order traversal works. We go to the leftmost part of the node, and then we go to the node, then we go to the node's right. Node here refers to the every node in the level of the tree, right? Okay, so let's quickly come back to the dry run. So here is the in-order code. I hope you know what is the in-order code, though I'll be typing it out after this dry run. So here the most important condition that we'll add is that if when we are working on the node, right, we need to just know that if it is a leaf, right, it is a Boolean function, and we'll pass the root here. If it is, then simply add it into the vector that is given to me right now, right? So just add its value here, right? Now I have mentioned something like is leaf, which is the second step of the approach. So I'll have one more function that will be a Boolean function. This is a void function, right? So I'll have a isLeaf function in which I have just passed the root, and I'm saying that if it does not have a left and it does not have a right, that means it does not have any children, right? So that means it is a leaf node. I have to return a true, else I'll simply return a false, that no, it has either one of them or both of them. So that means it is not a leaf node. So after this, now let's dry run this whole approach here. Now what I can see is I first of all, I'll be given root 1, and suppose I have given v1 for root 1. So I'll be following the in-order traversal. So for the in-order traversal, what happens is I am on 3, right? So 3 would say I am following the in-order traversal. Just keep me, will work on me later. Go to the left part, right? I'll again write here in order is left, then we go to the root, then we go to the right. So 3 is saying go to the left. I'll say okay. So I'll come here, 5. So 5 will say go to my left. I'll say okay. I'll go to 6. So 6 says I do not have any children, right? So that means I am the node in consideration. So we'll check this condition, that is it a leaf node? It will say yes, I am a leaf node, and we'll add 6 into the vector, and it pops out from our recursion stack space, and we return. As soon as we return here, we go to 5. Now 5 is the root node, right? So before going to the right, I'll first figure out, I'll do my work for the root node because I'm following the in-order traverse. So 5 will say, now you have to work with me. So I'll go here, I'll say is leaf, and I'll know that no, it is not a leaf because it has kids, right? So I'll say, okay, so you are not a leaf, I'll not add you, and I'll just quickly remove you from my stack space. Then I'll now go to 5's child, that is 2. So 2 will say add me in your stack space. I'll be like, okay, I've added you into the stack space. After adding 2 into the stack space, I see that it has a left. So I'll go to the left. Now left does not have any further child. And I'll say that is it a leaf? Again, we'll check it. We'll say yes, I am a leaf. We'll pop it out from the recursion stack space as add it into our vector v1. Then we'll go to 2 and We'll again, now 2 is in consideration. 2 will say, no, I am not a leaf node. We'll simply pop it out from this recursion stack space. We'll go to 4 and 4 will say, yes, I am a leaf node and I'm the only one. So you need to consider me. 4 will be added here and we'll simply return. So the left subtree has been completely visited and we've gone to every node in the tree and we figured out which all are leaf nodes and are required for further processing and they've been added into the vector, right? So now I'll go to the right. So here again in my so now before going to the right, I'll figure out I still have 3 left in my recursion stack space, right? So I'll say, okay, now let's pop out 3 and let's see that is 3 a leaf node. It says, no, I am not a leaf node. So like, okay, don't worry. We'll just pop you out and let's go to your kid. So we'll come to 1. As soon as I come to 1, it's like figure me out later, go to my left side. So like, okay, let's go to 9. So 9, now for 9, we do not have any kids. So say, yes, it is a leaf node and we'll add it into our vector V1. We'll go back from 9 to 1. We'll figure out 1. 1 will say, no, I am not a leaf node. Why? Because I have kids. So we'll simply pop it out from the recursion stack space and then we'll go to 8. Now 8 will again say that, yes, I am the only one and I'm a leaf node. Add me in. So this is the vector that we will have, vector V1 at the end of the approach that has been followed for the first tree that was given to us. Now what I'll do is I'll quickly make another stack space here, right? So that it is not a lot messier for you people to understand. So yeah, let us consider this would be this is for root 1, right? Now this is for root 2. So I am here on 3. I am again following the in order traversal. So I have a vector and the root that has been passed to me, that is the second root, to the in order function, and I'll be traversing and figuring out what will be the answer. So I am on the root, is add me in your recursion stack space, but first go to my left side. Like, okay, 5, like I have a left side, okay, 6, I do not have any children. It is just me. You need to figure me out. Like, okay, you are a leaf node. Let's add you in. So I'll add 6 here. Now I'll go back here on 5. So 5 will say, you're following in order. Figure me out first before going to the right side. I'm like, okay, are you a leaf node? He says, no, I'm not a leaf node. So what we'll do is we'll simply pop it out from the recursion stack space. We'll go to 7. Now I'm here on 7. 7 will say, yes, I am a leaf node and I'm the only one, so you need to add. Like, okay. So we'll go back to 5. 5 will go back to 3. We have 3 in the recursion stack space. And before figuring out the right part, I need to figure out 3. So I'll say, okay, so pop out 3. It is not a leaf node, it will not be added. Right? We'll go to 1. 1 will say, okay, you have me, but figure out my left child first. We'll go to 4. So 4 will say, I am a leaf node and I'm the only one, so you need to add me. I was like, okay, I've added you and I've popped you out from the recursion stack space. I'll go to 1. 1 will say, I have children, so I am not a part of the vector. I'll not be a part of the vector. Just pop me out. I'll, okay, we'll go to now. After 1, we'll go to 2. So 2 will say, okay, you have me, add my child left node 2. We'll have 9. So we are here. After 2, we were here. 2 said, call my 9 first, then figure me out. So I was here. Now 9 will say, I am the only node that you need to consider. I do not have any children, so I am a leaf node. Add me in. We get a 9 here. We figure out 2. 2 is not a leaf node. It has children, so will not be added. We'll go to the right part. So right has 8. So 8 will be added because it is a leaf. And then we can simply compare these two. And we'll have the answer as true, which is the output that is required, right? So I think the approach should be quite clear to you after this. Now I'll quickly switch to the Leetcode platform and we'll quickly code this up. Okay, so here is the question. I've been given two nodes, that is the two roots, right? So simply what I can do is I can create two vectors, right? V1 and V2. And what I'll do is I'll call in order with root 1 and say V1. And then again I'll call in order, that is root 2, and I'll call V2. And then I'll simply say at the end of it, you just return me that are these two similar or not. So here now let's create the in order function quickly. I'll be getting a tree node root, right? And a vector int ampersand v. Time if I do not have a root, I'll simply return, right? Then as I'm following in order, which is left root right, so I'll say if the left exists, in that case, take me to the left child, right? And the vector remains the same. Now here, for the root, when we're working with the root, that means the particular node in consideration, I'll say if it is a leaf, right, simply pass in the root. Then in that case, you push the root's value in the vector that is given. And I'll say if the root right exists, then again call the in order function, give roots right and v. So this is the in order function. We need to create the is leaf function. It will be a Boolean function, is leaf, right? We're giving it a root node and we're simply saying that if at any point of time the left child, there is no left child and there is no right child for the given root, you will say yes, it is a leaf node. So you'll return a true, else you'll return a false. I think we're good to go. Let's run it and see if it's working fine. And I guess it's working fine. Let's submit it and let's see what happens. So yeah, we can see that the code is working fine. Talking about I'll quickly copy paste it. Now, this is the code that we have just worked upon. So now let's talk about the time complexity and the space complexity. So if you see for the time complexity, we are going for a DFS that is happening twice. So that means if I have one tree, it has n nodes, right? I have the second tree that has m nodes. So I'm traversing all of these nodes, right? That means I'm traversing n plus m nodes, right? Each time. For example, this was my first tree, right? This was the first tree and the second tree was something like this. So I'm traversing n nodes here and m nodes here and I'm figuring out the child one, right? So figuring out the child one would not add into the time complexity, just traversing all of them will. So I'll have the time complexity as O of n plus m. Talking about the space complexity, as we are having a recursion stack space, I showed you in the code, in the approach that we did, that how a recursion stack space is formed, and always it has the, it's like size is always equal to the height of the tree. So assuming that the height of the first tree is h1 and h2 is for the second tree, the height of the second tree, this would be the recursion stack space that would be formed. So the space complexity turns out to be O of h1 plus O of h2. And if, for example, we had skewed trees, so in that case, the worst time complexity would further reach to O of n plus m again. Why? Because in a skewed tree, we'll be again going through all the nodes, right? We're going to left, left, left. So the recursion stack space increases a lot, right? For a balanced one, we'll have O of h1 plus h2. That means you got to a left, you came back again. But for a skewed tree, for example, if you had something like this, right? So 1, 2, 3. Okay, I'll just write it here. 3, 4, 5. So one will say, okay, you have me, go to my left. The two, you have me, go to my left. Three will say, you have me, go to my left. So you see the stack space is increasing, right? It is increasing. So that is why the worst case time complexity is n plus m, and the best case is h1 plus h2, O of h1 plus h2, where h1 and h2 is the height of tree 1, height of tree 2 respectively. Thank you so much for viewing the video till the end. Please like, share and subscribe. Thank you.